Hello everyone. Today we are going to talk about the composition profiles developed in the interdiffusion zone. Last two classes in the context of interdiffusion, we talked about what are the driving forces for interdiffusion. Then the previous lecture we gave a lot of examples about the phase formation in the interdiffusion zone. We understood that only the single phase regions develop in the binaries and so on. Today, we are going to see how do we sketch the composition profile given that we know what are the phases that are forming. In practice, it may be reverse. You may see the composition profile using an SEM or EPMA. We will talk about the techniques also later in the coming weeks, and then you guess the phases. So that's why it is important to know what is the correlation between when you know the phases and how is the composition profile in the interdiffusion zone should look like. So these are the concepts covered. We also have to understand what is the chemical potential variation. This we had introduced the concept in the lecture 11. Then we will take two examples in this lecture, one of isomorphous system, one with the narrow intermediate phase, and also if possible we will also go to the wide intermediate phase regions. These are some keywords. So let me start. So first is isomorphous system. I think all of you are aware what a isomorphous phase diagram look like. We have also seen this in the previous lectures. So this is the very simplest schematic of isomorphous system, where you have a complete solid in one region. Here you have liquid plus solid. This is actually wrongly marked. Let me just correct it. This is should be the liquid phase here, and then you have the complete solid solubility as well as the complete miscibility in the liquid. There is a region of liquid plus solid that exists. So let me just cross this so that there is no confusion. So now with such a isomorphous system between A and B, let me choose two alloys. One alloy P, which has the composition here XB P, and another which is the composition XB R. So these are the two alloys. So let me form a diffusion couple using these two alloys. So this is how it would look like. You have alloy P, which is the A rich, and alloy R, which is the B rich, and we place them in contact at time t is equal to 0. Now, when I am forming the diffusion couple, let me also understand before I tell how the phases develop. Let us see how the chemical potential of each of A and B are in this alloy. So, to sketch the chemical potential variation, I already told you before that we see that let us draw this free energy versus composition curve here. So this is represented in the green color, and since we are talking about temperature T, the phases we are only drawing the solid free energy curve. We are not drawing the liquid, but liquid will lie somewhere at the top because the stable phase here is the solid phase. Now, what we do is we mark the composition of the alloy P here. So this is the alloy P, and the free energy is Gp. Then we mark here the alloy R, and the free energy is Gr. And to know what is the chemical potential, we draw the tangent at this alloy P. So if it intersects here at the A axis, this is what gives us mu A in the alloy P. And this is mu B in the alloy P, or we should say mu A in this phase. The reason I have written P is because P is a single phase. So that's why, just to distinguish, I have written P. But please remember that chemical potential is always defined for a component in a particular phase. Then for the alloy R, similarly we draw a tangent here. So you see this is where it intersects the axis B. So this is mu B in R, and this is mu A in R. as we discussed in the first lecture of this week, that the chemical potential gradient is the one which drives the interdiffusion process. So, you can clearly see that mu B in R is greater than mu B in P, and mu A in P is greater than mu A in R, which also in this case coincides with your concentration gradient. That is, the concentration of B is higher in R and concentration of B is lower in P. So, therefore, based on the chemical potential differences, we can say that the diffusion will happen. So, the A will move from P to R because A is higher here, and B will move from R to P. So, this is the direction of the flux. So, this will be the situation at any time, let us say T2, and you see that there is some unreacted P, there is some unreacted R here, and there is this zone which is called as interdiffusion zone. And we have also indicated that mu A in P is actually greater than mu A in R. That is the reason of the direction of this flux. And eventually, if if we keep this process happening for infinite amount of time, eventually what you will see is that the whole system will come to a composition which is given by this point, which is represented as XBQ, and the free energy of this is represented by this point. So, this you can see that here this will be the situation at t equal to infinity. Why should this happen? Because if this was the case initially at t equal to 0, the free energy is represented by this point, which is GQ prime, but the reduction or in free energy is achieved when the interdiffusion happens and you obtain a total composition corresponding to Q. So, it is this free energy which is driving the process of interdiffusion, which is also reflected in the change in the chemical potential gradient. So, now if I have to ask you that let us see how the composition profile looks like at this point or at this instant T2 in the interdiffusion zone. I know that there is a solid solution here, there is an alloy which is P, which is alloy which is R. So, now if you look at this composition profile, I have drawn it here for different times. So, this is the first one is the simplest t equal to 0. This is our initial interface, which is represented by a dashed line. So, here you see that initially the B has the composition, or initially in this block the composition corresponds to XBP, which is here, and after the interface it corresponds to XBR, which is here. Let us say in between 0 and T2 there was some time at T1. If we draw profile, the B will continue to move from R to P. So, therefore, you will see that there is this region here which is now getting depleted in B. The composition is less than XB of R, whereas on the other side it is getting enriched in B and the composition is higher than XB. As you move or as we proceed more with the annealing duration, as the time increases to T2, you will see that more and more B has moved from R to P. So, you can see this is the line for T2. So, here the composition becomes now more less than XBR, and here the composition is increasing with respect to XB. And if you allow an infinite time so that the equilibrium is actually attained, then at t equal to infinity, the entire assembly will have one single composition which corresponds to XBQ. So, this is how you can draw a composition profile, or you can understand the composition profile and the interdiffusion zone correlations. Okay. So, you need to understand the system, what was the initial phase diagram, have the chemical potential gradient understood so that it helps you which direction the diffusion will happen, and then you can draw the composition profiles. So, now moving ahead, we saw also the example that there is possibility that in the composition or in the isomorphous system, it is also possible to have what is known as miscibility gap. Okay, what is miscibility gap? We represent it something like this here, where you have a alpha solid solution, but in a certain temperature and a composition range, or below a certain temperature in a certain composition range, the alpha doesn't exist as a single phase alpha, but it exists as alpha 1 plus alpha 2. Remember that alpha 1, alpha 2 all have the crystal structure same. It's only the compositional differences, and the composition of alpha is given by this point, and composition of alpha 2 is given by this point. So, this is alpha 1 composition, this is alpha 2 composition, and any point in the miscibility gap, you have a mixture of alpha 1 and alpha 2. Their fraction may vary, but the composition of alpha 1 and alpha 2 remains the same. So, please remember, let us say if you have a point here and a point here, the 2 points will have different fractions of alpha 1 and alpha 2, but the composition of alpha 1 and alpha 2 in that mixture will remain same. So, now if we try to see how the composition is here. So, suppose if my annealing temperature is T1, okay. So, this is the situation which is for the annealing temperature of T1, okay. So, let us draw here T1, and now here in T1 what we have is T1 is a temperature which is completely in the miscibility range, okay. So, there is no gap here, this is a completely single phase solid solution alpha. So, this is how what is represented here, and you have n members A, you have n members B here. So, the composition will continuously vary something like this. So, towards the end it reaches 1 here, it is 0 here, we are only plotting xb. So, because this is pure metal, so it is varying from 0 to 1. Now, if you take the example of the diffusion couple which is heated at T2. So, the same diffusion couple, if we heat at T2, what would happen is that, so let me just indicate first that it is the temperature T2. So, this is the temperature T2, and here what happens is, remember we talked about in the lecture 11, I think, that two phase regions cannot develop in a interdiffusion zone of a binary diffusion couple. So, it was lecture 12 actually, and therefore, you will not see a alpha 1 plus alpha 2 region. What you will see is a phase alpha here. So, this region, and another phase alpha with a different composition here. So, it will be same alpha phase, a single phase alpha, maybe with different compositions existing here, and therefore, the composition profile will have a break. Because here what will happen is that you will have this alpha solution which will keep on increasing composition till it reaches this point. So, till it reaches this point here. Then onwards, no composition as a single phase is stable. So, therefore, then the single phase composition only starts from here. So, therefore, you start seeing the profile like this. So, in the miscibility gap, you will not have alpha 1 plus alpha 2 region, you will not see in the interdiffusion zone. What you will only see is a break or a jump in the composition profile. So, remember, this is a jump, this dashed line does not indicate there is a composition, it indicates only the jump. Okay. So, hope that is clear to all of you. Now, there are often phase diagrams where you have intermediate phase developed in the interdiffusion zone, or rather in the phase diagram there are not just one, several intermediate phases may exist. I will just show you a simple example where only one intermediate phase is there. So, you can see that there is an intermediate phase beta. Right now, you don't need to worry about P and Q. We will just talk about it shortly. For you, now you see this phase diagram where this is an intermediate phase beta which exists in the phase diagram of A and B. Now, suppose if I want to draw the free energy versus composition diagram at this temperature T, how does it look like? So, this is my green color phase is the GA. Why we are writing GA here is because there is no terminal solid solubility. If there is a terminal solid solution alpha, we can write G alpha here, but right now we have just written GA. Similarly, GB is written here, so this point. And the intermediate phase, because it is only existing for a short range of composition, so it has a free energy diagram which looks like this. So, that is represented by beta. Now, for this equilibrium A plus beta, you draw a common tangent here like this. So, and this common tangent, if you extend here, it gives you mu A, and here in the alloy mu A here, and here it is mu B. Okay. Now, if I want to sketch the composition variation of a chemical potential, remember that in this region, in this entire two-phase region, you will have only one common tangent between the beta and this A. So, Ga and G beta, if you draw a common tangent, in this entire composition range until here, you have one single common tangent, and therefore, in this entire region, the mu B or mu A will remain constant. See, here in this entire region, you have A plus beta existing together. And what is the condition for the equilibrium of two phase? That for each component, the chemical potential should be equal in each of the phases. So, therefore, the mu B will remain constant in this entire region. Similarly, mu A will remain constant in this entire region. Then there will be a slight jump. So, then here there is a slight jump here, a very steep jump rather, and this chemical potential will go up to mu B2, this value here, and that is because of the equilibrium with the B element here. So, in this entire regime again, the chemical potential is constant because you have a two-phase region here which is beta plus B. So, this variation of chemical potential is there. So, now if I make a diffusion couple between A and B, there is certainly a chemical potential difference. The mu B is somewhere here and mu A is somewhere here, and therefore, you will see that you can have the flux of A coming from A to B and flux of B coming from B to here. So, you will see that in the A mu B is 0, in the B mu B is maximum, and therefore, there is a difference in chemical potential of B. Similarly, there is a chemical potential difference between A, and therefore, the diffusion will happen from 1 to 2 for A element and 2 to 1 for the B element. This is more straightforward, and we understood this now. So, this is the situation at T1. But how will the composition profile look like? So, when you draw the composition profile for this, be careful, because here even at T1, so this is the situation at T equal to 0. So, remember at T equal to 0, you have pure A here and pure B here. So, if I am sketching XB, the XB is 0 here and XB attains the value of 1 here. But at T1 also, you remember that you have only beta phase developed here. Okay, you have only beta phase, single phase beta developed here, and beta has almost negligent variation in the composition, and that is the why you will see a constant line in the interdiffusion zone. So, at T1, you will have initial region where the composition will correspond to XB is equal to 0. Then there is a jump, Unlike the isomorphous case where there was a continuous development, here there will be a jump, because the composition now reaches to the composition of beta phase, which is this here, and it remains as long as there is beta phase in the interdiffusion zone, then it again jumps to this B. So, hope that is clear that in the interdiffusion zone, if there is a phase with a very narrow intermediate, there is a narrow intermediate phase, that means the composition range over which that phase exists is very narrow. You will almost see a horizontal line here. One may argue that okay, there is slight bit of range here, but that is very small. Practically in microscopes you will see that it appears as a constant or a horizontal line. So, now let me come back to this question of or this reference to this alloy P and Q. Suppose if I make a diffusion couple instead of A and B like we did in the previous slide, if I make a diffusion couple with the alloy P and alloy Q, remember we did this similar thing in the isomorphous system. We made alloy P and alloy R, two alloys diffusion couple we made. Similarly, if I make a diffusion couple one with alloy P and another with alloy Q, in which direction you think the B will diffuse? You understood the question, I hope. So, suppose let me just try to represent it here. So, suppose if I make a diffusion couple of alloy P and alloy Q and heat it to the temperature T, in which direction you think the B will diffuse? Before you proceed with the video, think for a moment because the answer is definitely there in the next second or so, but you please pause and think for yourself that in which direction the B will diffuse, whether it is P to Q or it is Q to P. So, the actual answer is there will be no diffusion of B that will occur. Why it is so? The reason is present in this diagram. So, if you see, this is the variation we draw in the last slide also. So, if you, this is where the chemical potential of B lies in the alloy P, and here it is the again the chemical potential of B in the alloy Q. And you see that in this entire region chemical potential of B is constant. So, there is no gradient of chemical potential of B in P and Q, and therefore, there will be no interdiffusion occurring between the P and Q. Hope that is clear to you. So, now let us move ahead with composition profile in the wide intermediate phase. So, these are the examples you will typically encounter in phases like NIAL or FEAL, which exist for a wider composition range, unlike the line compound or the compounds we just schematic we saw, where it exists over a very narrow range. So, the phase diagram looks something like this. So, here we have represented, you see that beta is exists as much more higher composition range. We have put alpha and gamma as well here. So, and at a temperature T, if you draw the free energy curve, so now you notice the slight difference in the way we draw the free energy curve. The beta now it is lesser steep because it can exist over a wider composition range, and when you do the common tangent construction, you will see there is a region of alpha, alpha plus beta, beta, beta plus gamma and gamma. Similarly, now probably it is clear from the previous discussion that any two phase region you will have the chemical potential constant, because the chemical potential of any element A or B has to remain same if the two phases exist together. So, therefore, if you sketch the variation of chemical potential, let us say of B, initially as the composition of B increases here, the chemical potential increases. Why it is so? We have seen a relation also that chemical potential is directly proportional to the composition. So, you here it will increase as the composition of B increases. Here because there is a two-phase equilibria, alpha plus beta, so you will have a chemical potential which is constant. Then in the B, there will be an increase in the beta, there will be an increase in the chemical potential of B again. And then again you have a constant region where you have beta plus gamma, and then again it is a single phase region. So, this is how the variation of chemical potential will be. So, suppose if you form a diffusion couple between A and B and you see alpha, beta and gamma phases, remember again here that we saw in the previous lecture that it is not necessary that all alpha, beta and gamma should develop in the interdiffusion zone. It depends completely on the kinetics. It may or may not develop. Okay. But let us say for the sake of discussion, in this case, you have all the three phases alpha, beta and gamma developed in the interdiffusion zone. So, now how will your composition profile look like? You will have a small region which will be constant here, the composition is 0. Then you have this region of alpha in which the composition will increase. So, you can see the composition increases till it reaches this point. After this, then you have the beta phase. So, remember the beta phase, the composition starts from here. Even in this mixture, remember the composition of beta is only here. Okay. So, the composition of beta is represented by this point. So, therefore, what you will see is a jump in the composition. So, here it will come to this point. Then there is again a gradual increase to the point here. So, within the beta phase, the composition increases to a point here, which is corresponding to this point in the phase diagram. And then again there will be a jump in composition and you will have the gamma phase starting, which is something represented by here this point, and then the composition of gamma will increase up to the this point here, after which it is pure B. So, the difference you can notice here that here in the beta phase, when there is a wide intermediate phase, you can also have a compositional gradient, whereas in the case of the narrow intermediate phase, it is almost appears horizontal. Okay. And if you have alpha and gamma also, so the composition variations look like these what are shown here. So, again it is not necessary that all the phases will grow, but if your interdiffusion zone is like this, then the composition profile look like this. And why this discussion is important is actually in practice, when you make a diffusion couple, you will not know what are the phases, but what you can measure in a SEM or a EPMA is this profile, and then correlate with the phase diagram. You will be able to say, okay, this must be alpha region, this must be beta, and this must be gamma. Okay. So, then we will continue further in the next class. Thank you for now. If you have any questions, please feel free to post it on the forum. Thank you.